Okay, hello class. Exciting because we are starting our next book, book 1.5, and new topics now. So we did a lot in book 1 with derivatives. That was sort of the key word for us there. And this time the key word is antiderivative, or another term for that is integral. So hopefully you see the sense that there's some relationships between derivatives and antiderivatives, or integrals. And so we're starting in chapter 1. And our goal in chapter 1 is to figure out how to get areas of unusual regions. So far in your math career, you've probably done some geometry, right? And you looked at how to get areas of squares, rectangles, circles, triangles, maybe trapezoids. Those are the most common shapes you probably learned how to get areas for, and those were always geometric regions. So classical shapes and the Greeks were really interested in these to figure out the area of these, what are sort of nice shapes. Even though there's some non-linearities with the circle and everything, they're still very basic shapes. And now what we want to do this time is get the area of unusual shapes. And so here's an example of unusual shape. It's got a lot of non-linearity. There's no, nice geometrical shapes in here. And so we want to get the area of this shaded region here. And this is doesn't fit one of the classical geometric formulas, so we're going to have to derive something new. And the shapes could be really unusual. I mean, that's like geometric up here. And now we're going to have to use calculus on the ones below. So like that region there, something like that. We could have weird sort of star-shaped things. Anything you can imagine, you might want to get the area of. And lots of applications for that we'll see, maybe not so much in business calculus, but often in engineering, even in like landscaping, amount of papers that I need, amount of paint to paint something. So even in art designs where we want to know areas of unusual shapes. Okay, so let's take a look at this one. This one, a couple of properties that we notice right away is that there is this function, y equals x cubed minus x plus 1. And then we shade from that function to the x-axis. And then we go between some bounds along the x-axis. So we go from x equals -1 to x equals 3. Well, that's the type of problem that we're going to be able to do. The area under a region, we'll put it over here, from y equals f of x to the x-axis, from some limits x equals a on the left side to x equals b. And so that's the one picture here, but suppose x was like, y was x cubed, and maybe we wanted to go over here from like -2 to 0. Well, that'll give us that shaded region. So you always go from the function to the x-axis when we're going to be doing this in our calculus method. So that's one restriction. Or maybe you want to go from -2 all the way up to 3, right? We'll be able to get both of those together combined. So one thing you might think on this, back to our original example, you might decide to divide this region into shapes that are familiar to you. You might say, oh, like this little section over here looks like a triangle, and it's sort of a triangle. I could do 1/2 base times height and get the area of that. Maybe you see like, oh, this is kind of like a circle in there. Maybe this part is a rectangle. And so you'll divide it into a bunch of shapes and then add those up. And that is what you're actually doing there is an idea related to Riemann sum. So one of the key terms we're going to learn over here in calculus is we will be computing something called Riemann sums. This mathematician named Bernhard Riemann, a German mathematician centuries ago, figured out a way that we could compute areas by shoving shapes that we knew the areas of or that were easy to compute into this region. And in fact, let me draw another copy of this. So Riemann's idea was that he would put shapes, and he would only use one shape. So let's say the easiest type of shape over here is probably the rectangle to get its area. Really simple formula, length times width. So he would divide this, shove some rectangles in here. So maybe he put this rectangle, something like that. So he would put, in this example, 1, 2, 3, 4, 5, 6 different rectangles, and we're usually going to call that n, the number of rectangles that we use. And you would say that the area, the exact area of the shaded region up here is approximately the area of adding up the area of these 6 rectangles. And you could have put more rectangles and you should get a better approximation, right? If I put a picture, put another copy of this below. If I made my rectangles skinnier, that should do a better job. There should be less error. And you can actually see the error visually as like, this is error, right? I didn't get enough there. I went over there. Underestimated there, underestimated. So that's your error, the visual error. And if I do, again, small, thinner rectangles, we'll see that there's less of that black shaded. Mine aren't really very uniform, but you get the idea, right? So again, if you did all the shading of the error, there's a lot less in this picture than there is. And if I keep adding more and more, I should get better and better approximations. And so again, Riemann's idea was to shove some easy shapes in there. Rectangles are easy to get the areas of. The more you add in there, the better your approximation. That's really the main idea for us. And now we're going to talk about adding a little more structure to Riemann's idea to get this area of the shaded region. So. And we're going to have different types of Riemann sums we're going to compute. And the main 3 that we're going to look at are the left, right, and mid rules. So I'm going to do these all for this example with n equals 4 rectangles. I'm going to do this 3 different ways. So let me draw a copy here. 3 times. Left. Right. And mid. And each time I want to put 4 rectangles in there, but I'm going to follow a different rule each time. And so for the left rule, it goes, the region goes from -1 to 3. And that's kind of convenient because it actually divides this into equally spaced units, right? They go from -1 to 0, 0 to 1, 1 to 2, 2 to 3. That's 4 subdivisions along the x-axis. And same thing for each of these, so I'm just gonna had they chose, if they had asked us to do 5 rectangles, we could still draw the picture, but it'd be a little annoying on the divisions because we have fractions. Dividing this space of 4 along the x-axis into 5 regions would be a little harder. 8 would be no problem because I just add, right, halves everywhere in there. Okay. But almost always they're going to ask you like nice whole divisions of this. Distance x goes from, usually again they're going to find area of the shaded region from y equals x cubed minus x plus 1. That's the function to the x-axis. And they'll always give you limits from x equals -1 to x equals 3, right? So those are a range on x. X takes 4 units across, And we're going to divide those into 4 subdivisions so they each have a width of 1. And just some notation you'll see later that delta x is the width of each rectangle. And that's always given by taking your right endpoint, which we usually call B in general terms, minus your left endpoint over the number of rectangles. So for our example, we'd say 3 minus a minus 1 over 4 rectangles is 4 over 4 is 1. So the width of each rectangle is 4. I'm sorry, the width of each rectangle is 1. Okay, then that divides our region. So I'm going to draw a line. Into 4 equally spaced regions. And then we'll come back and draw the heights of the rectangles. We know the width of each rectangle is always 1. Now for the left rule, to get the height of the rectangle, we go to the left side of the first interval. So that will be over here, where my thumb is. Go to that side, go up to the function. Here's our function. On the left side, go up to the function, and that will be your height. Now the next one, I go to the left side of this next subinterval. That's this part over here with my thumb. I go up to the function there. That becomes the height of that next rectangle. The third one, go to the left side because I'm doing the left rule. That becomes the height. Last one goes from 2 to 3. The left side of that is at 2. I go up to the function at 2. That becomes my height. Next example, on the right, same idea, but we're just going to use the right side every time to draw our rectangles. So the first interval goes from -1 to 0. 0 is the right side of that interval, where my finger is. I go up to the function. That becomes the height of this first rectangle. So I'm actually dragging it backwards this time. From 0 to 1, 1 is the right side of that interval. I go up to the function there. That will become the height of the second rectangle. One more time. 2 is on the right side. Go up to the function there. That becomes the height of the third. And last for the fourth. So what do you think happens for the mid? Rather than using a left or a right endpoint, you're going to use a mid endpoint. So the midpoint would be right here. Between -1 and 0, the midpoint's at -1/2. I would go up to the function there. That becomes the height. So the midpoint of every interval becomes your height. The next one, between 0 and 1, the midpoint is at 1/2. I go up to the function there, draw a horizontal line. That becomes the height of the second rectangle. Third one, midpoint. That becomes the height. Fourth one, midpoint. That becomes the height. And this is how we always do these 3 rules. These are the most common and the ones you need to know. The left, you always use your left endpoints for every interval. Right, always use your right endpoints. Mid, always use the midpoints to create the heights. Now, if you just look at these 3 for this example, which one do you think out of these 3 is going to give the best approximate area with just using 4 rectangles? You can look at if you want to go ahead and draw in the error. This first one underestimates, the second one overestimates. Maybe they sort of cancel each other out. Underestimate, underestimate. So we think this one should be an underestimate, just looking at the picture of the exact area. The exact area is here. This one looks like it's going to underestimate it. For the next one, the first rectangle for the right gives an overestimate. Second rectangle, underestimate. Third one, underestimate. Maybe those two kind of cancel each other out, but this next one's a really big overestimate. And so we would say that this one looks like it would overestimate the exact area. So we come in too low, we come in too high. Here's our exact area. Maybe you should average those. That'd be a good idea for folks that have are taking like a stats class, maybe you understand that concept. Now the mid rule, let's look at that. The first one has, it actually splits its error. Some overestimates, some underestimates, maybe a little bit more on the over. Next one, a little over. Third one, a little under and a little over. Fourth one, same thing. So this one, it's harder to tell whether it overestimates or underestimates, but of the three, this one should be the best. And in fact, for almost every application, every function that I could give you, the mid rule almost always gives you the best answer out of these three. There's other better ones, even better than the mid, that they're just mentioned in the journal. You don't have to know how to compute them by hand, but like Simpson's rule or trapezoid rule do even better than these. Okay, that's the picture, but now we actually want to go ahead and compute our approximate areas. So we've got some intuition on whether we expect it should, how good it should be, and whether we think it's an over or underestimate. But let's actually do the computation. And this isn't hard. This is just geometry. It's kind of tedious, but we're just going to, for each one of these, add up the area of 4 rectangles. So we're going to get length times width, plus length times width, plus length times width, plus length times width for each one of these. So let's start with the left rule. For the left rule, we're going to get the area of each rectangle. They always have a width of 1. So the area of the first rectangle is going to be 1 times the height. So the width is 1. Now, what was the height of this? So the height was, I went to -1 and went up to the function. Well, that's just asking about the height of the function at -1, which is just saying I need to multiply this times f of -1. I need to say 1 times f of -1. So we'll come back to getting that, because here's our function, y is a function of x. We can also call that f of x. So we need to get f of -1. Well, actually, let's go ahead and do it while we're here. -1 cubed is -1. -1 times a negative is a +1, plus a 1, so it's a +1. So it turns out that this area is 1 times 1, which is 1. So the height of this first rectangle is 1. I'm sorry, the height is 1 and the area is 1. Let's do the second rectangle. So this one also has a width of 1, so that we're going to take 1 and we'll multiply that times the height. The height for this next one is we went to 0, went up to the function, so the height is f of 0. So now I need to plug in 0 here. F of 0 is 0 minus 0 plus 1. So that also has a height of 1. So the area is 1 times 1 is 1. Okay, we move on to our third rectangle. How did we get the height there? We know the width is 1, so the area is going to be length times width. So the width is 1. Multiply that times the height. What is the height of this rectangle? Think about how you drew it. You went to the left side at 1, went up to the function. So I need to get f of +1 this time. That's 1 minus 1 plus 1. And that's 1 again, it looks like. Hopefully this last one gives us a different number. This last rectangle also has a width of 1. By design, they always have the same width. We multiply it by the height. The height is f of 2 this time. F of 2 is 8 minus 2 plus 1, so that's 9 minus 2 is 7. So this one's actually much taller than my picture shows. The picture is not to scale. And then we would add up 1 plus 1 plus 1 plus 7. That gives us an area of 4 rectangles, and we'd say that the left approximate area is equal to 10. And that should be an underestimate of the true area. Now we'll do the same thing for the right and the mid. So each case, the area is always 1 times something, 1 times a height. And we just have to figure out what the height is. So the height of the first one, we actually went to the right side. We got f of 0. So we need to figure out what f of 0 is. Back to the function, 0 minus 0 plus 1 is 1. So we need to do 1 times 1 is 1. So the area of this first rectangle is 1. We move on to our second rectangle. The height was derived from the right side. We went up to the function, so we need to know what f of 1 is. Come back to our function, plug in 1 for x. 1 minus 1 plus 1 is 1. So third rectangle, we go to the right side. We went to 2, up to the function, created our height. F of 2, we already did that. Let's see, that was 8 minus 2 plus 1, which was 7. The last rectangle, the height was at 3. So we need to get f of 3. F of 3 is going to be 27 minus 3 plus 1. So is that 24, 25? That's a much taller one. So the area is 1 times 25 is 25. Add these up. 1 plus 1 plus 7 plus 25. The right approximate area is, what is that? 9, 25, 34. So in this one, we thought was going to be an overestimate, just looking at our picture. And again, if your picture is drawn to scale, you can get a better sense. So our true area at this point, we can say we know lies somewhere between 10 and 34, but that's a big range. We should be able to do better than that. So now we're going to come over here to our mid rule. The mid rule, we're going to need to do area is 1 times a height. Each case, the width is 1 times some height. 1 times a height. And so we need to figure out what are the heights that we're multiplying these widths by. So in the first one, think about how you got it. You went to halfway between minus 1 and 0, which is minus 0.5, and then went up to the function. So I need to do this. F of minus 1/2. So that's minus 1/2 cubed. Minus 1/2 plus 1, that's minus 1/8. Minus 1/2 plus 1, turn them all into eighths, and we'll have a minus 1 minus 4 plus 8, which is 3/8. So 3/8 is what goes here. 1 times 3/8 is 3/8. So the area of this first rectangle is 3/8. The second rectangle, we went halfway between 0 and 1, which is a half, went up to the function. That height is an f value, so we need to get f of 1/2. So come back up here, do a little bit more arithmetic. F of 1/2, 1/2 cubed, minus 1/2 plus 1 is 1/8, minus 1/2 plus 1, let's put them all over eighths. So it'll be 1 minus 4 plus 8 is 5/8. So the height of this second rectangle is 5/8. You multiply the 5/8 times the width of 1, and you get 5/8. Continuing on, we have the next rectangle, the third rectangle. We went halfway between 1 and 2, which is 1.5. Went up to the function there. So we need to get f of 1.5, which is the same as f of 3/2. So do a little more fraction work. F of 3/2 is 3/2 cubed minus 3/2 plus 1. So that's going to be 27/8 minus, turn that into eighths as well, minus 12/8 plus 8/8 for a total of how many eighths? Minus 4. 27 minus 4 is 23. So the height of this third rectangle is 23/8. We take that and we multiply it by the width, which is 1. Easy multiplication gives us 23/8 as the area of the third rectangle. One more to do. a little more work with fractions. So we're going to get f of 2.5, which is also 5 halves, f of 5 halves, which is 5 halves cubed, minus 5 halves plus 1, which is 125 eighths minus 20 eighths plus 8 eighths. And that is what? 105 plus 8, 113 eighths. So the height of this next one is much bigger. It's 113 eighths. Multiply that by the width, which is 1, and we still get 113. So I need to add up these 4 things. And that'll give me my mid-approximate area using 4 rectangles. And we'll say that that is, let's see, what is that? 113 plus 23, 1, 3, 6, plus another 8, 4, 144 eighths. Which is what we can divide by 2, 72 fourths, divide by 2 again, 36 halves, divide again, what is that, 18? Oh, okay, so it looks like it turns out 18. So now we say our area somewhere between 10 and 34, probably closer to the 18. We think that's a better estimate using just 4. Again, we know if we did 8, 20, 50 rectangles, a lot of work, but we could do it. It's not hard, right? It's just tedious. It's not hard computations. You're just doing lengths times widths and adding them up. So let's go ahead and see, now that we've done these different rules for this problem, let's look at what it looks like visually. So I want to show you a couple tech tools. So the first one, let's go to Desmos Riemann sum. Again, this is called a Riemann sum. I'm just going to Google on Desmos Riemann sum. Desmos is the graphing calculator we introduced before. And there's some nice, so folks have designed some nice tools to help us visualize Riemann sums. So let's put in our function instead of the f of x they have. We had x cubed, x caret 3, go down to minus x plus 1. Right, that's our original function. Good. And we wanted to go from the left side. A was minus 1 to B, oh, B is 3. Okay, so that's the same one. I'm going to zoom out so we can see the whole thing a little bit better. Oh, it's much steeper than I had drawn in my little picture there. When you go to minus 3, it gets really steep quickly. And then n, the number of rectangles we were doing was 4. So here's our picture. And then you can change the rule, the choice of the method here on the left. Set C equals 0 for the left, set C to 1 for the right, and C to 0.5 for the midpoint. So right now it's showing, C to, type it in, C is 0 because we want to do the left. Okay, and then the left rule, we kept computing, our picture didn't look quite right because I didn't draw it to scale, but we kept computing having an area of 1, 1, 1, and that does show because these first 3 rectangles, if I zoom back in a little bit, those first 3 rectangles always have the same height. See, this first rectangle here has a height of 1. The next rectangle has a height of 1. The third rectangle height, and it's not until we get to the fourth one where we have a different height, in this case, a height of 7. So this shows the picture for the left rule, and then I come in here and type C equals 1 for the right rule. And there's our picture, which again, we also showed that the heights for the first 2 rectangles were the same, which it shows here. They each have a height of 1. Then the next rectangle goes from 0 to 1 and also has a height of 1. The third rectangle goes from 1 to 2 and has a height all the way up here of 7. And the last rectangle, so again, height of 7. You can see that right there on the axis, the y-axis. The last one goes from 2 to 3 and goes way up there, has a height of 25. So again, we can see that. We just keep dragging this down. There's our height of 25. And so it's adding those up. And it's showing right here in this I value is what it's calling I. is the area of 34 for the left. That's what we got, that checks. And if we go back and just put our left rule, and we had C was 0, we got the value of 10. Again, that's showing what we got here is 10. Let's do one more. Let's put the midpoint rule, which we set C to 0.5. And when we do this, we get a, oh yeah, that's my arithmetic. I got 18 and they got 19 right here. Let's check. I must have done something with my arithmetic. 72. Must have one of these fractions off. One of my fractions must be slightly off. But you can see the picture too for each of those. And let's see what happens when we make n bigger, right? So our approximation should improve with the midpoint rule, and you can see that visually that it's getting, there's less gap between the little green and the black function, right? They're getting better and better as I make this. And it's no problem for the computer to program this. This is easy, right? And look down here at the I, the approximation for the mid rule with 33 is like 19.98. And notice that it's converging towards values. It looks like when n is 50, we're really close to like 19.9936. Maybe it's going to get closer to 20. And it looks like this will let us go all the way up to n equals 100. And we're getting, again, kind of closer to a value of 20. So we might guess the exact area is 20. But we won't be able to determine that until chapter 2. We'll have a way of getting exact areas. For now, we're just doing it approximately with Riemann's idea of a Riemann sum. Okay, next tech tool I want to show you is Wolfram Alpha. Yes, Desmos doesn't like when you leave. It always asks. So Wolfram Alpha, you can actually type in what you're trying to do. There are a couple tech tool pages that also have these instructions in your journal. But you can say, I want it to do, for instance, the right endpoint rule for the function y equals as is x cubed minus x plus 1. So the caret takes it up. You can see their examples in extended keyboard if you're trying to figure out how to type something in to enter it. On the interval from, we can put in an interval notation if we like, -1 to 3, or you can actually type it out, x equals -1 to x equals 3, with, let's say, n equals 4, and yeah, and we did the right rule with, I think we just say 4 intervals is how Wolfram likes to read it. Okay, we'll learn this stuff here, symbolic form and interval, when we get to chapter 2, I think. So we're not ready for that. Right now, we're just trying to see, it shows the left endpoint, gives a value of 10, the right endpoint of 34, the midpoint rule of 19. We'll talk about the errors later. We're not ready for that just yet, a couple of videos from now. So you can see it compute with the different rules, the approximation, check that the function you've entered correctly, check that your endpoints were correct, and then the number of intervals you're trying to divide it into is all correct. And again, you can easily ask it to do like, I don't know, 400. Computers don't mind that. It would take us days to probably do that computation, right? That's really tedious. And it gets an estimate with the right rule of 20.12. It shows what the other rules would have done, the left and the mid. Again, we briefly mentioned the trap in The Simpsons. There's plenty of other ones that try to get even more and more precise. But they take, a little bit more complicated work to do those. Okay, and then there's one more tool, GeoGebra, that you can use. That you could also just Google GeoGebra Riemann sum calculator and play with the settings there. So let's just do that real quick. Lots of different options, different teachers submit things. You can try different ones. This one has the left and the right. You can change the function, change your values for A and B. We were looking at from -1 to 3 of x cubed minus x plus 1. Right function x cubed. Okay, there's our function. This is showing with 10 and the left rule what the approximation is. Again, you could make it 20. And you can just keep seeing how the left rule always forms from the left side of the intervals to get the heights, as opposed to had we done the right always goes from the right side of every interval to get the height, the right side to get, so sort of dragging it back where the left is dragging it forward. This one doesn't have the mid, but again, if you've gone back and tried another one of these calculators, it might. Get another one, and they all show the nice picture for it. Okay, this one has several left midpoint. We won't talk about the lower sum and upper sum, but you can go in and change the function, play around, watch what happens as you increase n, and watch the picture. And this is a good way to make sure you are drawing your pictures right, because the pictures really help you. If you can draw the picture correctly, that is very easy to see what's the left and what's the right, what's the mid. So I think that visualization is a great tool to help you as you're working through chapter 1. Okay, so next time we'll come back and we will be talking about other ways to improve this and then a narrow analysis. But have fun with the first video and going through the first several pages in chapter 1 of journal 1.5. All right.